Today I am going to explain one of the most important concepts in advanced data structures, heaps, specifically the types of heaps, their properties, operations, and examples. Heaps are widely used in priority queues, scheduling, and heap sort. Let us begin. There are mainly two types of heaps based on how the parent node compares with its children. 1. Max Heap. 2. Min Heap. In this presentation, we will learn both types in detail along with examples and algorithms. A max heap is a complete binary tree where the value of each parent node is greater than or equal to the value of its children. This means the root node always contains the maximum value. Max heaps are used in applications like priority queues, heap sort, and CPU scheduling. The key properties of a max heap are: 1. It is a complete binary tree, meaning all levels are completely filled except possibly the last one. 2. Each parent value is greater than or equal to its children. This is called the heap property. 3. The maximum element is always at the root, so accessing it takes O(1) time. 4. Since the tree height is log2n, insertions and deletions take O log n. Heaps are usually stored as arrays, not as pointer-based trees. If a node is at index i, then left child index 2i plus 1. Right child index 2i plus 2. Parent index i1/2. Here is an example array. 50, 30, 20, 15, 10, 5. This corresponds to the following tree structure. 50 // 30 20 // 15 10 5. This is already a valid max heap. The array 50, 30, 20, 15, 10, 5 represents a valid max heap. We will use this example for insertion and deletion operations. The steps to insert a new element into a max heap are: 1. Insert the element at the end of the array. 2. Perform heapify up, which means repeatedly comparing with the parent and swapping if it is larger. 3. Stop when the heap property is satisfied or the element reaches the root. We start with the original array. 50, 30, 20, 15, 10, 5. We want to insert 40. Step 1. Append 40 to the end. 50, 30, 20, 15, 10, 5, 40. The tree looks like this. 50 // 30 20 // 15 10 5 40. New element. Now, 40 is at index 6. Parent index equals 6 to 1 / 2 equals 2, whose value is 20. Since 40 greater than 20, we swap them. New array. 50, 30, 40, 15, 10, 5, 20. Tree. 50 // 30 40 // 15 10 5 20. Now 40 is at index 2. Parent at index 0 is 50. Since 40 less than or equal to 50, heap property is satisfied. Thus, insertion is complete. Final array. 50, 30, 40, 15, 10, 5, 20. First, we increase the heap size by 1 and insert the new element at the last position of the heap. This is done to maintain the complete binary tree property. Next, we compare the inserted element with its parent node. If the inserted element is greater than its parent, we swap them. This swapping process continues upward, comparing the element with its parent at each level. We repeat this until either the element reaches the root or the max heap property is satisfied, meaning the parent is greater than the child. This process is called heapify up or percolate up. Finally, the element is placed in the correct position, and the max heap structure is maintained. Extract max, or deleting the root, follows these steps. 1. Replace root with last element. 2. Delete the last element. 3. Perform heapify down by swapping with the larger child. 4. Stop when heap property is satisfied. First, we check whether the heap is empty. If the heap size is 0, we display a message saying heap is empty and stop the operation. If the heap is not empty, we store the root element, which is the maximum value, in a variable called max. Next, we replace the root element with the last element of the heap. After that, we reduce the heap size by 1, effectively removing the last element. Now, the max heap property may be violated. To restore it, we perform a process called heapify down or percolate down, starting from the root. We begin with this heap. 50, 30, 40, 15, 10, 5, 20. Tree. 50. // 30, 40. // 15, 10, 5, 20. We remove 50, the maximum element. To keep the tree complete, we replace it with the last element, 20. New array. 20, 30, 40, 15, 10, 5. Tree. 20. // 30, 40. // 15, 10, 5. Now compare 20 with its children, 30 and 40. Larger child is 40. Since 20 less than 40, we swap them. New array. 40, 30, 20, 15, 10, 5. Now 20 has one child, 5. Since 20 greater than or equal to 5, heap property holds, so we stop here. The final heap after deleting the maximum element 50 is 40, 30, 20, 15, 10, 5. Now 40 is the new maximum at the root. Now I will explain the peak maximum operation in a max heap. In a max heap, the maximum element is always stored at the root node. The peak operation is used to view this maximum element without deleting it from the heap. First, we check whether the heap is empty. If the heap size is 0, we print a message saying heap is empty and stop the operation. If the heap is not empty, we simply return the root element, which is stored at index 1. This is because the root always contains the maximum value in a max heap. The peak operation does not modify the heap structure and does not perform any swapping. Therefore, the time complexity of the peak maximum operation is 1, since it directly accesses the root element. This operation is very useful when we only need to check the highest priority element without removing it. The time complexities are: insert O log n, extract max O log n, get max O 1. Important applications of heaps include priority queues, CPU and task scheduling, heap sort, graph algorithms like Dijkstra's shortest path. Thank you.